electrochemistry. Have we discussed any oxidation reduction yet at all?
A little bit.
A little bit. Okay, good. All right. So it's probably worth my going into the details and just assuming that you don't know anything. So when we're discussing electrochemistry, we're talking about those reactions in which electrons must be transferred between species. They transfer from one reactant to another reactant in the process. And we have some special terms that are assigned to what happens to the species. So if we transfer an electron from this one to that one during the process, then this one is said to be oxidized because it loses an electron. And this one is said to be reduced because it accepted an electron, received it. And these two processes always occur together. They're never separate. If there's an oxidation, there has to be a reduction, and vice versa. And we also have another term. If this one is oxidized, then it causes the reduction of this one. And as a consequence, we call it the reducing agent. You can probably figure out where this is going. If this one's reduced, it causes the oxidation of this one. So it's the oxidizing agent. All right. All right, and there's a little mnemonic to help you remember these if you need it. Oil rig. Okay. Oxidation is loss. Reduction is gain. I even use it sometimes. All right, so in order to determine whether electrons are transferred, we need a bookkeeping scheme for assessing who's got the electrons. All right, so these are the rules. Rule number one: for a reactant or a product that is a non-charged element, its oxidation state is 0. So if we had something like this, like my space shuttle reaction, and let's see, we need 2 of these, maybe 2 of these. These are gases, and standard conditions, that's liquid. All right, so these are elements in their standard state, and they're not charged. So we assign them an oxidation state of 0, and we put the oxidation state, at least in this class, we put it in a place where you would find a charge. All right. So if there are any ions involved, say we had, I don't know. Trying to think of a good example. If we had sodium chloride in aqueous solution, or no, let's do it this way. Let's go back to our solubility product. If this is a solid and it's going into solution, then it's going to split up into ions. Yeah, ions. Okay. The oxidation state for these would be the charge. Okay. Well, as a matter of fact, this solid is made up of ions too, so their oxidation states would be their charging. Okay, those are the easy ones. Now we start having to make assumptions. Because if we're going to calculate the oxidation state of some element in a reaction,
if we don't fix some of them as unchangeable, then there's no way to calculate them all, because you got to have everything but one unknown, right? It's just like algebra. If you've got one unknown in the equation, you can solve for it. But if you've got two unknowns and only one equation, you can't solve it.
Okay, so the next rule has to do with oxygen. Oxygen in a compound is assigned an oxidation state of -2, except in the case of peroxides. A peroxide is two oxygens bound together and then anything else on the outside. So these two together are a -2, but each one is a -1. Okay. Otherwise, oxygen is always -2. Oxidation state. And keep in mind, this is a bookkeeping scheme. This doesn't mean that oxygen has a charge, because these assigned oxidation states can occur for covalent compounds. Right? For instance, water. Right? This would be, that's the oxidation state of oxygen. So what would that make hydrogen? Hydrogen would have to be a +1, right, to balance the oxidation states, just like we balance charges. And that's probably the next rule. Yeah, hydrogen. In covalent compounds, hydrogen is a +1. Unless, well, in covalent compounds, in ionic compounds, hydrogen is usually the second element, and it's paired with a metal. So if that's the case, and our example here is aluminum hydride, this makes hydrogen a -1, and aluminum is a 3+, just like we learned when we were naming compounds, right? +1, +2, +3. Okay, so there are some similarities between charges and oxidation states. But some elements can have different oxidation states, and that's why we're laying down these rules so that we can calculate them. Let's see, we just dinged in. I have to expand it a little bit. There's Michelle and Emma. All right. We are a class now. Okay, so that takes care of hydrogen. Fluorine is always -1. Any compound that fluorine is in, whether it's ionic or covalent, fluorine is counted as -1. And you'll notice on your, not on this periodic table, but say in your review document. If you look in your review document at your periodic table, you may have already noticed this from the very beginning. Each one of those little squares has several possible charges in it. It looks like charges, but those are actually oxidation states. It only charges if they're metal non-metal combinations. Otherwise, they're oxidation states. So that's why you can see something like chlorine has 1, 2, 3, 4, 5 values that's possible. Those are oxidation states. But you'll notice that fluorine only has 1. Yeah, fluorine is -1, always and forever. Okay. For neutral compounds, the oxidation states must add up to 0. So like I said with water, right? If oxygen's -2, hydrogen has to be +1, so we get a 0 summation. Okay. If we have a polyatomic ion, then the oxidation states must add up to the charge of the polyatomic. For instance, I don't want to steal my own thunder. Let me find one. How about nitrate? Polyatomic ion. Right? We know that oxygen has been given 2 minuses for each oxygen. That makes 6 minuses total, right? Okay.
we got to hold one of those out for this negative right here. So that means we only have to balance the 5 minus by that nitrogen. So we can say 5 plus for that nitrogen is its oxidation state. And this is a covalent compound, so to speak. It's a polyatomic ion, but it's covalently bound. So these are not charges, but these are oxidation states as assigned in our bookkeeping scheme. So that's the way I assess the oxidation state in a polyatomic ion. I hold one of those charges out for this one. And if it's a 2 minus, I hold 2 out. If it's a plus, I add 1. And then continue with the balancing. We'll do some practices. Alkaline metals and alkaline earths, they're always like the charges you would find in an ionic compound. Right? Alkaline metals, first column is +1s. They're always +1s. Alkaline earths are always +2 oxidation states. Let me see, why did I put this one in here? When chlorine or nitrogen are present with none of those above compounds. Oh, okay. So for instance, if we have this one, we haven't assigned a value. Right? So if this is the case, then we give chlorine a -1 so that we can calculate phosphorus. If we have something with nitrogen in it, like this one, we haven't assigned nitrogen in our rules. So we're going to say that nitrogen is 3 minus. Because of where it's located in the periodic table, right? -1, -2, -3. Okay. So the only reason we do that is because we have to, right? Otherwise we're stuck. And carbon can have 8 different oxidation states. No, 9. Are they listed? No, they're not. They're not all listed, but you can get anywhere from -4 all the way up to +4 and anything in between for carbon. So it makes sense to assign 3 minus to nitrogen because it doesn't have quite the range. Now this system of oxidation states is best used in inorganic chemistry wherever possible. When you get to organic chemistry, then we're going to talk about something else we may have mentioned. I don't know if I've mentioned it before, is formal charge. We talk about that? No, okay. So that works better for organic compounds and organic chemistry. But for inorganics, the oxidation state seems to work fairly well. And I'll say it again, this is just a bookkeeping scheme. All right, so let's try one out here. Potassium dichromate. Okay, so alkaline metal. There you go. Oxygen. Okay. So we're going to calculate what's chromium. And this means that there's 14 minuses for the oxygen and 2 pluses for the potassium, which gives us a total of 12 minuses. Okay, so we have to balance that. Since this is a neutral compound, we have to balance that with 2 chromiums. That means both of them together have to be 2 plus. Each one is a 6 plus. Okay, let's see, is this animated? Yeah, it's animated. Okay, now we have a carbonate ion. Okay, oxygen again. Right, so we have a total of 6 minus, but we have to hold a couple of them out for that one. So we really only have to, oops, get ahead of myself. We only have to balance 4 minus with this carbon. There we go. And you can prove that it's right by just saying, right, 3 times 2 minus 6 minus, and a 4 plus means 2 minus left over. So we're good. There we go. We must have done some of this because naming compounds, you got to be able to calculate the charge. Right, so for this one, probably old hat. 2 minus, this is 4 minus, this has to be a 4 plus. So we would say manganese 4 oxide. All right, PCl5. Right, if we're going to assign a -1 to chlorine, that means that phosphorus has to be a +5. And SF4, right, fluorine is always -1, so that means sulfur has to be a +4 in this case. All right. Stop me if you have questions. All right. So, in order to determine where the reduction occurs and where the oxidation occurs, we need to assign these oxidation states to each of the elements in the reaction. And the reaction doesn't have to be balanced. The elements, the ions, the compounds, the polyatomic ions, though, must be written correctly. So we have this. Let's see, let me do it over here. We have this equation which is already balanced for us, right? But it doesn't have to be in order to assess what we're going to do with it next. So we have the reactants on this side, products on that side. And very often you'll find in these redox reactions, we'll leave the spectators out. Right? So that that manganate ion probably had, that manganate ion probably had some counter cation with it to balance its charges when it went into solution. And that iron, it probably had a counter anion with it. We just leave them out because they don't matter. So what we're getting at now is a method for balancing equations called half reactions. Right? And it's very simple. 1/2 reaction is reduction, and the other half is oxidation. But you've got to figure out where those, which species belong in which equation. That's the key. Now, this one's already been done for us. I don't know why I left this slide in here, because it can be confusing. Because what it is, what you'll normally be given is, say, this equation would have started this way. If you see it like on an exam, how about that? You would have seen this one and this one, and then charges 2 plus, right? Yields this one and this one, just like that. That's all you'd be given, and you'd have to balance the equation. Okay. So what we would have to do is assign oxidation states. Well, these are easy, right? They're charged elements, right? Ions, that's okay. Yeah, that's it. The only one we have to determine is this one, right? With a 2 minus for that oxygen, we have 8 minus, hold 1 out, right? For this charge. That means this one is 7 plus. Okay. Now we have oxidation states on all our elements. We can see where the elements were gained and lost. Okay, so if we go from this manganese to this manganese, how do you get from a +7 to a +2? You have to gain electrons, right? You're going from a big positive to a smaller positive. You got to balance out 5 of those positives with electrons. So we would say gain 5 electrons per manganese. Okay, and that accounts for oil rig. Reduction is gain. That's the reduction step. That means this one is probably the oxidation step. So we would have lost 1 electron per iron. Okay. Now what you can do is separate these out, and they've already done it with the balanced equation, but it would look something like this. For the reduction step,
you would pull out the reduction reaction. This one. Minus. And I'm gonna put this one way over here so we can sort of line them up eventually. And we have the manganese 2+ here. Okay. Then oxidation step would be here. And we would say this would be Fe 2+, and it leads to Fe 3+. Okay. So, let me get my hard copy so I don't drift too far off course. I'm just checking to see if this is gonna pop up later. Otherwise, I'll go ahead and finish it and give you the rules while we're at it. So the rules for balancing by this method are that you set up the equation with the reactants and products as given, and then you assign oxidation states, and then you follow the lines and figure out which one is oxidation and which one's reduction. And then you write those separate equations. Okay. Now we put in the electrons. I believe that's the next step. I want to be consistent. Oh, there it is. Oh, we're gonna, yeah, the electrons weight. For each half reaction, balance all the elements except hydrogen and oxygen. Okay, so we got one manganese here and one manganese here. That's good. One iron here, one iron here. That's good. Okay. Then you balance the oxygens with waters. So if you've got 4 oxygens on this side, you need 4 oxygens on this side. There you go, 4 oxygens. Okay, everybody with me? Okay. So we've added 8 hydrogens on this side. Now we have to put 8 hydrogens on this side. Okay. All right. So we don't have any oxygens down here, so we can leave that as it is. Once you've got that done, then you add in the electrons. Okay, so we got 1 manganese here going to this manganese 2+. This is a 7+. And we have 5 electrons gained by this one. That means they occur here on this side. Because they're here and then they disappear because they're over here now. Okay. On this side, the electrons have to go on the other side. Okay. So this one lost an electron, it shows up as a product. Okay. Yeah, okay. So now what we want to do is balance the electrons for both reactions. In this case, it's easy. You got 5 electrons up here. We just need to multiply this whole equation times 5 in order to get 5 electrons there. Right? So this would be a 5 here, 5 here, 5 here. And we used up that 5. Okay, now the electrons are balanced. When we add these 2 equations back together, then the electrons cancel out. And you don't see them in the final balanced equation. Now we can bring everything down. So we're going to have one of these minus, and then we're going to have plus 5 Fe2+, and then 8 hydrogens. Did we use everything up? 1, 2, 3. 1, 2, 3. Then on this side, we have manganese 2+. We have 5 iron 3+, and we have 4
waters. Okay. Is that what they got? Yep, in a different order. That's how they got that balanced equation, was by this method. And this is balancing equations for acidic solutions. See those hydrogens? You can do this for basic solutions, but it takes an extra step. And I'll show you that in a few minutes, but heads up, all you have to do is once you've got it balanced for acidic solutions, you just add hydroxides to neutralize this one. So we'd add 8 hydroxides on this side, 8 hydroxides on that side, and then finish balancing it out. There you go. I call it the fake acid method because you do the acid first. Okay, so those are the rules that I was just following right there in green and blue and white. Okay. And there's a flow chart. If you find it useful, you're welcome to use a flow chart. All right, so here's another one. I think we can do this one. So this is what you've been given. Dichromate. And sulfite, SO3, 2-. And these are all aqueous. The other point that this method is making is that in aqueous solutions, water is an active participant. And it is not just a holding place. Water is a reactant. Let's see. Now to be sure, there are redox reactions that don't occur in aqueous solution. Right? With sodium, metal, and chlorine gas together, they're going to be violently react to give you table salt. Right? No water involved. Let's see. 3+ and sulfate. Okay, so first thing we have to do is assign oxidation state. Right? This one's easy. It's already done. Or while we're over here, right? We have 8- there because oxygen is 2-. It's 8-, but we have to hold 2 of them out. So we only need 6+ for that. Okay. And this one is 3 times 2- is 6-. We hold 2 out. This one is 4+. Can we do this one before? I think we did this one before. We'll do it again. 7 times 2- is 14-. Hold 2 out. 12-. So that means each one of these is 6+. Okay. So to go from, make some room here. Let's put this over here. I need to go from here to here. So what happened? 6+ to 3+. Gain or loss? It's not a trick question.
Gain.
Yeah. Gain 3 electrons for each chromium. I always put that in there because sometimes it's like this and sometimes you got subscripts. So we haven't got to balancing those yet. It just tells us for each chromium, that's what happened to it.
Okay. Why did you take 2 off for the SO4? Right there instead of 1 like the previous problem.
Because I need to end up with a 2- charge. So 2 of these are reserved for that charge. And I only need to balance these with that sulfur. So you can satisfy yourself. I mean, 4 times 2- on oxygen is 8-. I'm not multiplying times this, I'm multiplying times that. So 8- and 6+ is 2-. Okay. All right. So let me get these out of here.
so now we've got that one. Oxygen didn't change. Sulfur. We go from sulfur 4+ to sulfur 6+. So if that's a gain, this one has to be a loss. What? 2 electrons per sulfur. Okay. So now we need to separate them out into their reductions and oxidations, half reactions. This is a good exercise also, this half reaction method, for what we're going to do later is electrochemical cells, batteries. Right? Batteries have separate reactions. This will occur in one cell, and this will occur in the other, and the electrons are transferred, not just willy-nilly in the solution, they're transferred to an external circuit so we can tap that energy. That's what batteries do. They take these half reactions and separate them. So that's why you have 2 poles on a battery. One pole leads to one side and one pole leads to the other side. Okay, that was just a teaser. Okay, so we need to write the reduction equation here. Right? Reduction is gain. Reduction is gain. So we need CR2O7 minus, that leads to CR3+. I'm going to leave out the aqueous part because it's all happening in water anyway. And then the oxidation has to be SO3 2 minus SO4. Okay. So we got oxygen in both of them, so we're going to have to do the water trick on both equations. This has got 7 oxygens. So we need 7 water. We've added 14 hydrogens. Now we got to put 14 hydrogens back on this side. Takes care of the oxygens and the hydrogens. On this side, we've got 1 oxygen here and 4 oxygens there. So we need an oxygen over here. Let me move this back. SO3. We need an oxygen on this side, just one. Just 1 oxygen, right? 3, 4, 4. But we added 2 hydrogens. There we go. Now we can balance the electrons. Oops, what did I forget to do? That was the first step that I missed. Everything else is okay. All right, so if this one's going to be a gain of electrons, reduction is gain, that means the electrons have to be on this side. And for each chromium, 3 electrons were gained. But we got 2 chromiums. So that's 6 electrons, right? Total. All right. How about this side? We lost. We lost 2 electrons. So the electrons have to show up on this side. And there's only 1 sulfur, 1 sulfur, 1 sulfur. So it's just 2 electrons. There we go. Now we got to balance for electrons before we can add them back together. Right, this one's got 6. We need to multiply this one by 3, don't we? So 3 here, 3 here, 3 here, 6 there, and 6 there. And we know we're good because that's 6 electrons and that's 6 electrons. Now when we add them back together, those electrons go out. And we've also got waters on both sides. I've got 7 waters over there and 3 over here. Okay, so these 3 waters are gone. And these become 4. Right? Because they're on opposite sides of the arrow. Okay, now we can add them back together. So we got CR2O7 2 minus plus 3SO3 2 minus plus 14. Oops.
Hydrogens too.
You got 14 here and 6 over here. So those 6 are gone. Now these are 8. Oh, excuse me, 8 hydrogens. Okay. So that's 1, 2, 3. 1, 2, 3. And then on this side, we have 2 Cr3 pluses and 3 SO4 minus and 4 waters. Okay. Now let's see if that's what they got. All right, so I got a series of slides that do all this, but I figure probably makes more sense if you see me do it on the board rather than flashing it up on the screen like that. But it's there for posterity. All right, so we got the electrons accounted for there. Right. They went ahead and did the electrons, 6 electrons there. I did them later. They're building up half reactions before you add them back together. And let's see. There, 3 of those, 8 of these, 2 of those, 3 of these, and 4 of those. Okay. So we're in agreement. We're either both right or both wrong. All right. So that's balancing equations with a half reaction method. Okay, and there's a key word you're going to see is when it tells you to balance an equation with a half reaction method, it's going to say acidic solution or basic solution. Yeah, we've only been doing acidic solution up to this point. Right, so yeah, we got a good bit of time. We could probably afford to do this one. I don't know. I've got 87 slides. Maybe I better let the slideshow do this one. Should use the same method. Let's check it out and see if it does. So, which one is the oxidation step and which one's the reduction step? That's the first test. Oh. You just skipped over everything, didn't it? Just gave us the answer. I didn't animate the solution to this one, apparently. Oh, here we are. Here. No, I didn't. Okay, do you want to work this one out? Okay, we can do that. Br minus MnO4 minus yields Br2 and Mn2 plus. And everybody else is aqueous. Okay, so what happens? Well, this one's 0. Right? Bromine is one of those diatomics. And so that's its standard state at 1 atmosphere pressure and room temperature. That's a 2 plus, that's a 1 minus. We just need to do this one. 4 times 2 minus is 8 minus, hold 1 out. So this one's 7 plus. Okay. Now we can assess our reduction and oxidations. So Br minus to Br 0 had to lose an electron, didn't it? To go from minus to plus to a 0. 1 electron per bromine. That means this manganese underwent oxidation. Oh, excuse me. Be consistent here. Oh, gain. Reduction, not oxidation. Gain. 5 electrons per manganese, right? Go from a 7 to 2. Okay, so our reduction step is this one. MnO4 minus and produces Mn2 plus. And our oxidation step is Br minus and Br2. Okay, so we don't have any oxygens here. And oh, 2 bromines. Well, almost missed it again. Okay, these are balanced, these are balanced. Now we can go to the oxygens. We need to add 4 oxygens on this side. That means 8 hydrogens on this side. There we go. Now we can do the electrons. So we had one of these, go to one of those, and this was a loss of electrons. Oh, excuse me. This was a gain. What am I thinking? This is a gain of electrons. 5 electrons per manganese. So we only have 5. This one was a loss of 1 electron per bromine. So these electrons are going to be on this side. Since there are 2 bromines, then we lost 2 of them. Now we need to have the same number of electrons in each reaction. How do you do that when you have we have 2 prime numbers, right? Cross multiply, right? 2 up here. And 5 down here. Okay. So that'll give you 5 times 2 is 10 and 2 times 5 is 10. Let me back this one out. Do like that. Okay, so we're going to have 10 here. We're going to have 5 there. And we're going to have 10 here. Okay. Now this 2 would be 2 here. 16 there. 10 here. 2 there. And 8. Okay. When we add them together, let's see, we don't have anything else we cancel. Electrons go out. Add them together. So we have 2 MnO4 minus. We have 10 Br minus. We have 16 protons. We have 2 Mn2 plus. 5 Br2. And we have 8 H2. So is that what we got? There's the MnO4s. There's the 10 Br minus. There's the 16 hydrogens. There's the 2 manganese 2 plus. There's 5 Br2s. Yep. And 8 waters. Here we go. That's how we got there. Think you can do that? Yeah, you can do that. It's got to be methodical. Step by step. Practice, practice. I'm not going to give you any that are undoable. At least not with our methods. Some of them can get pretty hairy. We're not going to deal with those. Okay, so how about basic solution? Basic solution is the same as acidic until you get to the balanced acidic equation. Then you make the change to hydroxyls. All right, that's why you've already seen this part up here. All this blue, we just added these steps down here for basic solution. Okay. This is a question that might occur to you. You may wonder, why don't we just go straight to hydroxyls? Why do we have to go through the acid step and then go to hydroxyls afterwards? What if you started by adding hydroxyls first instead of hydrogens, right, to balance the oxygens? And
and the hydrogens. Could that work? Yeah, it could. Right? And we're just balancing equations. But what are the possible problems? Well, then once you've added the hydroxyls to compensate for the oxygens, then you got to add waters instead of hydrogens, right? But the acid method, you add water first and then hydrogens. With the hydroxyl method, you'd have to add hydroxyls first. I mean, otherwise, what's the point? I mean, it's a basic solution. So you got to start with hydroxyls. Then you have to add water on the other side. Then you'd have to balance any extra hydrogens because water's got 2 hydrogens each. It could become more complex, actually. I think the fake acid method is probably the more reliable one. Okay, so we've got this one. We want to balance it in basic solution. Is this one animated? Let me see. Oh, okay. I'm behind. No, it's not. It just gives you the answer. Okay, so we need to do this. Okay, Cn minus. Now, how do they know that this one is basic solution and not acidic solution? Any ideas? I mean, we're gonna balance it. We're gonna balance it as acid first and then convert it to basic. Why can't we just leave it acid? They put these things together in the lab and stuck a pH meter in there or a piece of pH paper. And they found the solution's basic, right? It's that simple, right? It's not complex. Right? So the reaction is telling them that this is basic. So in order to have the overall equation for that reaction, it needs to be balanced in basic solution because that's what the solution's telling you. Okay, so let's do oxidation states. Let's see, we don't have any elements here, so let's start with this one. All right, remember nitrogen had to be -3. So this means we hold out a minus for that charge. This means carbon is +2. Okay. This one we did before. What was it? +7. Let's do it again. 4 times -2 is 8 minuses. Hold out, yeah. So that's pluses. There we go. This one. Oxygen would be a 2-, obviously. And then we're going to have to assign nitrogen to be 3-. Right? Otherwise, we can't solve for the carbon. And the carbon is probably, since we did this one 3-, then we got to do that with 3-. Carbon is the one that is is undergoing one of the oxidation reduction. So that means -5 total, right? Got to hold one out. So it's 4-. This is a 4+. And actually that makes more sense because look what happened to carbon. If we do it this way, carbon lost 2 electrons, right? It's to the left of nitrogen. It's less electronegative. It's the one that's more likely to lose electrons than nitrogen is. If we tried to do it to nitrogen, then carbon would have to stay the same, and that's highly unlikely based on electronegativity alone. Okay. So I'm just justifying my actions here. All right, so this one is 2-, 4- total, so this has to be 4+. All right, now we have our species. Let's assign oxidation reduction. Let's just go ahead and do it like this. Reduction, oxidation. So the reduction is going to be the one that reduction is gain. So who gains? This one gains. 7+ to 4+. It had to gain 3 electrons, didn't it? Yep.
Okay, so we put this one up here, MnO4, is that a minus? Yeah, it's a minus. Kind of hiding down there next to the aqueous. And then we get that one leading to this species. Okay. Let's see, I'm gonna write that one there. And then the oxidation step is Cn minus. Cyanide becomes. Let's see what that would be called. I don't know. I'm sure it's got a name, but I can't think of it right now. It's just close. So it had to lose 2 electrons to get there. Okay, balance the non-oxygen, non-hydrogens. Right. These are good. 1 carbon, 1 nitrogen, 1 manganese, 1 manganese. Okay. So now we can do the oxygens. Justin got 4 oxygens. We need 2 more over on this side. Okay. So that means we need 4 hydrogens. On this side, we've got an oxygen over there. We need an oxygen over here. But now we need 2 hydrogens over here. Okay. All right, now electrons. Right, this one had to lose, gain 3 electrons per manganese. And there's only 1 manganese, so that's it. This one had to lose 2 electrons to go from a +2 to a +4. 2 electrons for each carbon, and there's only 1 carbon. So that's it. Now we need to balance. All right, we've got a 3 and a 2, another prime number situation. So cross multiply. 2 times this one, 3 times that. Okay, so we're going to put 2 here, 8 here, 6 there, 2 there, and 4 there. And then we're going to put a 3 here. So we use that one up. 3 here, 3 here, 3, 6, and 6. Okay. So now we got 6 electrons on either side. Those are going to go out. We've got 8 hydrogens here and 6 hydrogens there. Those go out. Leaves us with 2 hydrogens. Waters. We've got 3 waters here and 4 waters there. So these waters are going to go out and leave us with 1 water. Now we can add them together for the acid step. We've got 2 MnO4 minus plus 3 Cn minus plus 2H plus. Okay, and we have 2 MnO2 and 1 water. Well, put the water over here. Plus 3 CnO minus. And plus 1. All right, so now we need to get rid of the hydrogens. So we're going to add hydroxyl. This makes 2 waters. And we got 1 water over there, so that water goes away. And this one becomes 1. So now we have 2 MnO4 minus 3 cyanides, 1 water, 2 MnO2s, 3 CnO minuses, and 2 hydroxyls. Let's see if that's what they got. 3 CNs, 2 of those, 1 water, yep. 3 CnO minus, 2 MnO2, and 2 hydroxyls. Okay. Now, during the first semester, we learned how to use the budget method to balance equations. Some of these redox equations can be balanced with the budget method. And you don't have to pay attention to the redox situation. But the problem with that is water. If water is going to be part of going to enter into the reaction, then if you're not given that in the budget method, then you can't balance it. It's got to be there. So the half reaction is the way we do redox equations, just to be safe. Okay, now we're going to take our half reactions and do something with it. This is the galvanic cell, named after an Italian, Galvani. What he did was he took, well, the modern interpretation is little coin-shaped pieces of zinc and copper, and he stacked them together. But in between them, he put thick pieces of cardboard that had been soaked in a mild acid, so that it would be conductive. And then he hooked an electrode to the top. I don't know, copper maybe on the top, zinc on the bottom. A stack, and brought the two leads together and got a spark. So he made a galvanic cell. So we give him credit for it. Like I said before, if you just put the two half reactions together in a beaker, then the electron transfers will occur, but you don't have access to the energy that's transferred in that process. You need an external circuit to take those electrons and route them outside one cell and into the other cell so that you can access those moving electrons. That's the idea behind a battery. The reaction, of course, must be spontaneous. If it's not spontaneous, then it's not going to do any work, right? We learned that last chapter. Where do these reactions occur? Well, the reactions occur between whatever electrode you put in the solution and the solution itself. It'll occur at the electrode. So if we have our two half reactions and we put them in separate containers, then we'll have an electrode. Sometimes the electrode participates in the reaction and sometimes it doesn't. Right? But the reaction will occur at the electrode because that's where the electrons are. They're either coming in or leaving. Okay. So we got electrodes here, and then we route them through usually through some kind of meter. And sometimes we'll have a light bulb attached. Right. Just to show us so we don't have to look at the meter if you see the light up. I guess it comes in unless it's an LED. And then you have your solution in here for the reaction. Okay, what's missing? That's not a circuit, right? What does a circuit mean? The circuit is a circle. It's complete. This is incomplete, right? You got going over here, out here, it stops. You need something to bridge between the two, right? Sometimes you use a salt bridge, something that'll transfer charge. Let's put it on this side, right? So a salt bridge will allow movement of ions and charges to transfer. Sometimes you can bring these two together like this and have a porous disk. And that will allow for movement of electrons without mixing of reactants. But if these are two different half reactions,
In other words, they don't share any components between the two. Then they have to be separated. If there are some cases though, where the reaction actually shares one of the reactants, is shared by both. In that case, you don't need a bridge, right? Just pop the hood on your car. Your lead acid battery is one of those types. It doesn't have separated cells. Well, it does. It has separated cells, but they're complete galvanic cells, and you have what is it? 6 of them. It's a 12-volt battery, and they're 2 volts each. So does anybody have electricity in here? Physics, electricity? Okay. When you get 2 batteries together, like that, and you have say positive, negative, positive, negative, positive, negative, and you hook them like this. Right? So what's your voltage here? Your voltage is additive. If this one's 2 volts, and this one's 2 volts, and this one's 2 volts, this one's 6 volts. Okay, that's a series connection. If you do a parallel connection, where you connect this one to that one and this one to that one, it gives you a longer life, but you only get 2 volts out of it when it's parallel connection. It's just a little free physics lesson. Okay, so you need some way to complete the circuit. All right. And there you go. The one that we're going to make next week is a salt bridge. Your salt bridge needs to have some way. In this case, you've got a salt solution. See, you got a salt solution in the bridge, and then you've got a plug on the end to keep from mixing this and allowing both components to mix together. All you need is a way to transfer charge, right? You don't want to transfer reactants and products. Right? So we're going to use potassium chloride in here. Well, instead of using a plug, we're going to make a gelatin, actually agar. Gelatin, I've tried gelatin, doesn't work. Gelatin's a protein. And I think if you make your salt bridge with gelatin, it undergoes its own redox reactions and changes the whole scenario. But agar is a derivative of seaweed. It is a thickening agent. Have you had micro? Micro? No. Okay. You have had micro? Okay. So you've made petri dishes and agar slants and test tubes, and those we're going to use that material, that agar, to thicken the solution, but it's going to have potassium chloride in it, so the ions are mobile. Okay. Now there's some resistance. That's the problem with this method. There's some resistance in that bridge, so you shouldn't expect to get the theoretical voltage that we're going to calculate later. Porous disk is more efficient, right? It only allows ions to move back and forth across that disk and doesn't allow mixing of the cells. That's more efficient. Okay. So for this galvanic cell, and let's see, we've got the salt bridge or the porous disk. I've seen some lab setups where you have these, you ever seen these plastic plates with wells in them? You can get 2 wells side by side, and you can put one solution in one and the other one in the other, and then stick your 2 electrodes in them, and they're kind of small, and that goes to your voltmeter. And then how do you connect them? Well, you get a piece of paper towel and soak it in potassium chloride solution and just lay it on there to make the connection. And it lasts long enough to make the measurement. And you can do several of these cells in those dishes, in those multi-wells. But we're going to make a big battery, right, in beakers. Okay. So by convention, the cell on the left is the one where oxidation occurs. Right? And the one on the right is where reduction occurs. Okay? So electrons are traveling this way. Going from this cell to that cell by way of the external circuit. And in order for the electrons to be released and move through this circuit, oxidation has to occur because oxidation is loss. Something over here loses those electrons and they're picked up by that electrode and go over to the other side where reduction occurs. So the electrons are coming out here, they're going in here. Oxidation, reduction. Okay, we got another name for those. Let's see, is it on the slide? Yeah, the anode is this side. The anode is where oxidation occurs. And the cathode is where reduction occurs. Okay. Just memorize it. I don't have a good explanation for that. Well, I could say something like that. No, that would just muddy the waters. Just memorize it. Anode is oxidation, cathode is reduction. Okay. I sort of got my animation out of whack here. That shouldn't show up until later, that E sub cell. So how do we calculate what the voltage is on one of these cells? Well, the oxidizing, if this is the side that's reduced, this is the oxidizing agent. And this is the reducing agent on this side. And the driving force, it's called a pull here. You can think of it as a push. Electrons are being pushed that way. I like it better, push than pull. But either way, it happens. And this electromotive force, this potential, the cell potential measured in volts, can be calculated. Now, the volts actually mean 1 volt is equal to 1 joule of energy required for each coulomb of charge transferred. Now, we introduced a new term here, coulomb. Coulomb is a measure of charge, and it's named in honor of a Frenchman who did work in this area, Coulomb. And it has its origins in the way electricity was being investigated at the time. So we're stuck with it. And it's not bad because we have ways to convert coulombs of charge to moles of electrons. And I'll give that to you in a second. Because for our chemical reactions, we need to know moles of electrons to do stoichiometry. So that's what the volt means. It's energy per unit charge transferred from one location to another. So you have to measure the movement. Oh, we got video. That's good.
A useful galvanic cell can be constructed by using zinc and copper. The anode is a zinc bar placed into a zinc sulfate solution. And the cathode is a copper bar placed into a copper 2 sulfate solution. The two solutions are connected by a porous sodium chloride salt bridge that prevents the two solutions from mixing but allows ions to migrate. Attaching the cell shows that electrons flow from zinc to copper. Because zinc is a more active metal than copper, it is more likely to lose electrons. For this reason, the zinc bar is oxidized, producing a zinc ion and 2 electrons per zinc atom. The copper ions in solution gain 2 electrons and are reduced to copper metal. As the reaction continues, excess positive zinc ions build up in the zinc solution. At the same time, the loss of copper ions from the copper sulfate solution creates an excess of negative sulfate ions. Positive sodium ions migrate into the copper sulfate solution from the salt bridge, while negative chloride ions migrate from the salt bridge to the zinc solution and maintain neutrality of the solutions. The reaction stops when the zinc bar or copper ions are depleted. The overall cell reaction can be written like this.
All right. So that's actually the battery we're going to make, the galvanic cell. So we had, let's see, we had copper on this side and zinc on this side. In this case, the electrodes were active participants in the reaction. They used copper sulfate over here. We're going to use copper nitrate. I think that's right. Yeah. And on this side, we're going to use zinc nitrate. Okay, so notice from that demonstration that the zinc is being depleted here. The zinc electrode is being reduced in mass, and you can measure the change in mass.
Melting.
No, it's not melting. It's being, the zinc atoms are being oxidized. So when they lose electrons, the ions migrate into solution. They go into solution. They don't stay on the electrode. They migrate into solution. And the electrons that it gives up transfer over here and are added to copper ions, which are plated onto the electrode. So this one gains mass, this one loses mass. In this scenario, right, where the electrodes are active participants, you can have reactions where they're not. Okay. There we go. That's better. So we mentioned cell potential. How do we determine cell potential? Well, you can use a voltmeter and measure it. Right? And that's how it was done originally. But we wanted a way to predict the theoretical voltage on any proposed combination of 2 half cells and determine whether or not the reaction is spontaneous. Right? So we need a reference manual, right, with half reactions in it, so that we can put them together any combination we want and determine what their voltage is going to be, whether it's going to be spontaneous in the direction we choose, or it'll be spontaneous in the reverse direction, just like our study of entropy. If it's spontaneous one way, non-spontaneous the other way. Okay, let me finish this slide on voltmeters. What does a voltmeter do? A voltmeter measures, well, it uses Ohm's law. Let me see if that's part of the slide. That's part of the slide. It's not part of the slide. Okay, Ohm's law. Let's see, voltage is, I was thinking of it this way. V equals I R. So actually, Ohm's law is stated in this way. Resistance is equal to voltage over current. current is so many coulombs per second. Coulombs per second is a measure of current. And voltage is just volts. And for any type of material that we identify as a resistor, that is, resists the movement of electrons, then we give it a value in ohms, which is volts per, and this 1 coulomb per second is equal to 1 amp. So many volts per amp is an interpretation of resistance in ohms. Okay, so what a voltmeter does is it has a standard resistor in it, in the circuit. And that allows it to use this equation to measure voltage, because it will interpret the current that goes through it and spit it out as a voltage on the meter. Okay, it uses a known resistance. Now, the problem with the voltmeter is if the current is very low, the voltage is very low, then you waste some of it in the process, right? So it's not as accurate a measurement of voltage. So for that, if you need high accuracy, use a potentiometer. In this case, a potentiometer has a voltage. Say you've got the spontaneous movement of electrons is this way. Well, if this is a potentiometer, this device itself produces a calibrated reverse voltage that opposes the movement of electrons. Okay. So the old versions of potentiometers you'd have to adjust it. You'd have a dial and you'd adjust the voltage until it's zeroed out, until no more movement. The current, there's no more current in the circuit. At that point, then you would check the output and it would give you a voltage. How much voltage did I have to apply to stop electrons from moving? Now that one, since the electrons are not moving, there's no loss. There's no loss of energy from resistance, from the movement of electrons, as there would be with a voltmeter. So the potentiometer is more accurate, but it's more expensive, and it has to be regularly calibrated, because if you're gonna reverse the voltage, you got to know that your voltage is correct in that device. So those are two different methods that we use. Voltmeters are easier, and that's typically what you'll buy off the shelf at Walmart or Lowe's. You have to use special order potentiometers. They're expensive. Okay. So, and actually, most of them, they don't even call voltmeters anymore because they do more than one job. They call them multimeters. And they're really very inexpensive. You can measure direct current voltage. You can measure AC current voltage. You can measure resistance. They even have one for just checking if the circuit is open or closed. Right? It's got a little beep on it. So you just put it on there. If it beeps, then you've got a circuit. If it doesn't beep, you got a broken circuit. And most of them you can adjust for amperage for the movement of electrons, and measurement of that coulombs per second. You can actually measure millicoulombs per second, or milliamps. You just change the dial, and it changes the internal circuitry for that. Okay, enough of that. So that's a voltmeter that we would use to test the voltage of the cell. Now we want to say, I want to describe what's required in order to set up these charts of half reaction voltages. Okay. Remember, oxidation and reduction never occur separately. So if we're going to have a list of half reactions, that's physically impossible. You can't measure half reactions independent of each other. So we have to have a standard, an accepted standard that is given the value of 0 volts. And that's the standard hydrogen electrode. First of all, the values that we report as standard reduction potentials. So in this chart, all the half reactions are written as reductions. So you're going to have something here plus electrons, 1, 2, or 3, and then something out here, which is probably going to be a negative. Or if this is a positive, it'll come out neutralized, whatever the case may be. If they're written as reduction potentials, so the electrons are always on the left. Okay. And the conditions for the standard values, the E zeros, always occur for solutions that are 1 molar in concentration. If there are any gases present, they're 1 atmosphere pressure and standard temperature, which would be 25 degrees C. These are always measured at those conditions. Now, obviously, we're not going to be running our experiments at 1 molarity. That's way too high for many cases. So later on, we're going to find out how to take the standard potential and calculate the actual potential that we should expect from our galvanic cell based upon the concentrations that we're given. Right, so that's where we're headed eventually. Okay, compared to what? Standard hydrogen electrode. Come on, there we go. And it's arbitrarily given the value of 0 volts. So if the half reaction on the hydrogen electrode is given 0 volts, no matter what it's paired with, then the voltage that you measure for the other side is the voltage that you give it, whether it's positive or negative. Because sometimes the reaction will run toward the hydrogen, the electrons will go toward the hydrogen, sometimes they go away from the hydrogen, depending on the half reaction that it's paired with. And we'll see that in the table right here. I think it's coming up. But it's in your book. Have you read that chapter yet? Have you seen those tables? Okay. That's only a partial table. I mean, if you go to a CRC handbook, that's Chemical Rubber Company, CRC handbook, and look up standard potentials, you're going to find pages and pages and pages of them. Right? This table gives you the most commonly used and the ones that we're going to rely on. So that means if the half reaction you're interested in, when you put 2 different half reactions together, you got to decide which one is the reduction and which one's the oxidation. If the one that you read from the table is the reduction, then you leave it alone. And the voltage that is given is the voltage you use in your calculation. But if you need to reverse it, it needs to be an oxidation, then you reverse the voltage, the sign on the voltage, before you put them together. Okay, I'll show you some examples. Okay, oh, by the way, yes, this voltage is an intensive property. It doesn't matter how big the cell is. It only matters that it's under these conditions, and it's an intensive property from then on. In other words, the voltage is the voltage, the standard voltage is the voltage for that cell under those standard conditions, and it doesn't matter whatever else changes. Right. As long as you don't change that, or that, then that's the voltage no matter how big the cell or how small the cell. So you can get dry cell batteries at the store. Right? You get the big D cells. Right? You can get the next, I think some people still use C cells. Right? Then you can get the, I don't even think I've never seen an A cell. I've seen double A's and triple A's. Right? They get smaller and smaller. They're all 1.5 volts. Right? Doesn't matter what size they are. They're all 1.5 volts. right? So it's an intensive property. Okay. So if you want to know which direction the reaction is going to go and which one is the reduction and which one is the oxidation, you need to combine them in such a way that the voltage that you add together for the two cells gives you a positive voltage. Positive voltage means spontaneous. Okay, we're going to prove it in a couple of slides anyway. But for now, that's enough. So here's part of your table, right? We're starting with the most positive relative to the hydrogen electrode, right? So let's see. So the most positive or most active is fluorine, right? 2.87 volts relative to the hydrogen electrode, positive hydrogen electrode. So this one would be, since hydrogen is 0, we add 0 plus 2.87, that's a positive value. That means this one is written in the spontaneous direction against the hydrogen electrode. If we did this one against this one, right, these two, right, this one is less, they're still positive, right? So which one would you have to flip to keep the value positive? You'd have to flip this one, right? Silver 1 plus would have to be on the left-hand side, and silver 2 plus and electrons would be on the right-hand side. So this one would be the oxidation or the anode. This one would be the cathode. And the voltage would be 2.87 minus 1.99. Okay, because you had to change the sign. Okay, and that's the way you would do it. Typically, if you're combining two of these, any two of these, the one above stays as is. It stays reduction. And the one below flips to oxidation. Okay, that's one way to look at it. I got another way to look at it. And it's been rolling off my tongue here, but I haven't made a point of it yet. So I'm going to make a point in a minute to emphasize that. And these are just examples. These are relative to the standard hydrogen electrode. So let's see, we're still not there yet. Our positive values are getting less and less and less and less as we go down the chart. And these are all reduction potentials relative to the hydrogen electrode. There's hydrogen right there. Okay. So this hydrogen is 2 H pluses plus 2 electrons, it's H2. Right? And how do they do that? Well, they use a gas. They use a gas under 1 atmosphere pressure. So depending on which side it is, you would have your solution here with H pluses here, so it'd be acidic. And then you would have your electrode would be a source of hydrogen gas. And it would be under 1 atmosphere pressure. And the whole thing would be at 25 degrees C. Right? And then there would probably be a platinum electrode in the middle because you can't connect, it's hard to connect a solid to a gas. If you want to clamp your wire onto a gas, good luck. So we would have a platinum electrode in the middle, and it would go over to the other cell, whatever it happened to be. So this would be platinum electrode. Platinum doesn't react. Right? It's just an electron transfer. So depending on which side it was, that reaction would either go forwards or backwards. Right? If we had this hydrogen electrode combined with anything above it, it would be flipped to where the hydrogen would be oxidized. And all these would stay reduced. And then anything below it, this one would be as is, it'd be like that. And then the rest of these would have to be flipped. Okay. So If I haven't thoroughly confused you up to this point. How do we use this stuff? There's the rest of it. Oops. Get that out of the way. So your book says, if you want to know the standard potential for a cell, you read the table and you say the potential for the cathode minus the potential for the anode, which is correct, right? Because the anode is going to be anything below. The cathode is going to be here, anode is going to be there, right? So you want to reverse the charge on this one. That's why it's minus. And anywhere you have like that, the spontaneous direction is going to have cathode above, anode below. Okay. If we have to multiply the half reaction by some integer in order to balance the equation, the standard potential is still the same, does not change. Right? You don't change the potential by multiplying because it's an intensive property. Right? It's not like enthalpies where you have to multiply by whatever you multiply by, charge or any of our enthalpies or K's, where you're doing the overall equilibrium constant, combining, and you have to multiply them together. Now, in this case, standard potential is standard potential no matter what you do to the reactions. We'll get to the changes that occur, and instead of doing E0, we'll do that one first, but then eventually we'll get to the actual E for a given reaction under exact conditions that are stated. But we need help with a new equation for that. Okay, so for this one, if we have Fe3 plus and copper yields copper 2 plus and Fe2 plus, what should that look like? Well, the half reactions, right? Fe3 plus is going to Fe2 plus, and that is a reduction. We have to add an electron. So we write it just like that and read that off the table, 0.77 volts. Then we write the other half reaction. In this case, is as a reduction, copper 2 plus 2 electrons is copper, but copper needs to be on the left-hand side because it's being oxidized. So we flip the copper around and change the sign. Okay. And then we can add them together. And for the standard potential, you don't have to balance the equation. Now later you will have to balance the equation because we need to know what's the stoichiometry, how many electrons are actually being transferred. That'll be required for determining the actual potential. But at this point, the standard potential, all you need to know is which one's the anode and which one's the cathode, which one needs to be flipped, and then add them together. So the overall voltage on this one would be wait a minute, there's more. There we go. The cell potential then would be 0.43 volts. Now, the other way that I alluded to earlier is rather than saying the cathode minus the anode, what you can do is you can look at your values. If you write them both as potentials, let's see, write them both as potentials, come on, sticky, as reduction potentials, and then change the sign on one of them and say, does that give me a negative or a positive total? Then change it back and change the other one. Does that give me a positive? Then that tells you which one needs to be flipped. Right? That's the way I look at it. Then I don't have to memorize that equation. But you're welcome to. That's fine.
I have no objection to memorization. Okay. Why should we care if the E0 doesn't change? Well, like I said, later we're going to see that we need to know the quantitative transfer of electrons. So calculating the exact voltage requires an equation that was developed by a German. I think his name is Nernst. How would you like to have that for your last name? I guess in Germany it doesn't throw anybody a curve, but in the English language it just sounds funny. Nernst, old Uncle Nernst. So we need to know the actual. To know the actual cell voltage, we need a balanced equation and the number of electrons that are transferred, the moles of electrons transferred in that balanced equation. And then for later on, if we want to run the reaction in reverse, remember our potentiometer, we applied a voltage to stop the electrons. Well, if you exceed that voltage, you can make the electrons go backwards. And you can run that spontaneous reaction in reverse. And that's a process called electrolysis. And that's how they do things like, well, they don't have them anymore, but they used to have chrome-plated bumpers on cars. And you may see them in antique shows. But you'll see these cars with chrome-plated bumpers. They chrome plate them through a process of electrolysis. They take the whole bumper, they put it in a vat of chromium ions, and they run the reaction in reverse and cause the chromium to plate out on the metal. Okay, that's one example. A whole host of different examples. Electrolysis is an industrial necessity for many of the modern conveniences that we enjoy. Okay. So let me see. It's a little after 10. All right. Let's see. You already took a break. Do you need a break? Okay. So let's see if we can. There's one thing that I don't emphasize in this class is what's called the activity series of metals. And generally speaking, when you hear this, and this is the only reason I'm putting it up here, is this activity series. is a list of metals, and they're in order of decreasing activity. And that is the ones that the more active metal is the one that's more likely to give up electrons. And if you know that activity series, then you can say things like, well, I want to build a cell with zinc and copper in it and say which one's going to give up electrons, which one's accept electrons. And you can do that. But I don't hammer that too much because we've got the table there. We don't always use metals, right? So now for this one, order the following from strongest to weakest oxidizing agent. If we're looking for the oxidizing agent, what does that mean? The strongest oxidizing agent will be the one that is, let's see, strongest oxidizing agent is most likely to be reduced. Okay. So which one's the most likely to be reduced? One that's highest on the chart. Right? That's their order. So strongest oxidizing agent, most easily reduced. So we order by the largest positive standard reduction potential, if possible. So for each one of these, we're going to look at the standard reduction potential. Let's see. The problem, notice the problem here. We could, come on. Iron is no problem. Right. Well,
Metals tend to not want to be reduced. They'd rather lose electrons. So that would be a problem. That would be a problem. This will be a problem because it doesn't want any more electrons. It's already got one. Now sodium, all right, it should be fine. It will want an electron. Chlorine, yeah, it wants to accept electrons. So when we write their reduction here, we find that we have to put the F, we have to write it in terms of reducing F2. So the F minus is on that side. And this one, we have to put the sodium on this side, which makes, okay, that's fine. The chlorine, reducing chlorine, yeah, that worked out okay. Fe3 plus reduced to Fe. So Fe is on this side. It doesn't want to be reduced. See what I'm getting at? Okay, so what are we going to have to do to make sense of these? Well, since we don't know the values for sodium, fluorine, and iron as for their reduction potential, we have to rearrange them. Right? So that's a possibility there for a fluoride ion. Right? Sodium has to be flipped around because it's in the list. Right? We have to go by the list. Chlorine, we leave chlorine alone. It's fine the way it is. And we have to flip the iron. Okay. So what we're saying is that the least likely to be reduced is probably going to be sodium. It's the farthest to the left. Right? It has the lowest electronegativity of this group. So the sodium ion itself is not going to want any electrons. It's going to be the least likely to be reduced. Right? I know that's, I can't even think of an actual example where it would be reduced. So this is very hypothetical. And the one with the largest positive potential is chlorine. Right? So it goes first. Right? So we're going to say iron is next because sodium's over there, iron's kind of in the middle. Right? So it's still a metal, but it doesn't have as small, it's got a higher electronegativity. So iron should be there. I left out, there's the caret, okay. Then this sodium, right? Oh, we got both sodiums up there, don't we? Right. So this sodium actually has a value, which is extremely negative. And is that everybody? Iron, sodium. Oh, fluoride. Where does fluoride go? Well, fluoride doesn't want to be reduced at all. I wouldn't think. So actually, fluoride is the least likely. Chlorine, molecular chlorine is going to be the strongest oxidizing agent. It's the most likely to be reduced. All right. So when we build this galvanic cell, I mean, who wants to draw that picture for everyone? We need a shortcut, a shorthand way of writing it, and that's called line notation. So we need to know how is line notation written in standard form so that we can interpret it properly. All right. The anode components are like the picture that we drew. Anodes on the left of the line, right? Cathodes on the right. So we write the anode components on the left for the oxidation and the cathode components on the right. Okay. We separate by a double vertical line. That indicates a salt bridge. So whatever we put over here is going to have a double line in between it. It's kind of like a barrier. I'm going to wait. Okay. So we have anode stuff over here, cathode stuff over there, and this represents the salt bridge of the porous disk. If we need one. right? If we were to write one of these for the lead acid battery in your car, it wouldn't have one of these. Because there's no salt bridge. There's no porous disc. It doesn't need one, right? So this would be missing. Okay. We would just put a single vertical line. The single vertical line actually means a difference in phase. So if you have a, and that's exactly what it means. Solid, liquid, gas, solution, right? Aqueous solution. Any one of those changes from one component to the next has a vertical line between. That means a phase change. The concentration of in aqueous solutions should be specified with the notation, because that will change. If the concentrations change, then the voltage changes. So here's an example. Here we have magnesium in a magnesium 2+ solution, right? So let me draw that up here like this. Magnesium solid. And then there's a phase change to the solution, which is magnesium 2+ in aqueous solution. We don't know the concentrations yet, so we assume that this is standard potential. And then this solution is bridged to the other solution, aluminum. And then there's a phase change there, and we have the electrode, the aluminum electrode there. Okay. So if the anode's on this side and the cathode's on this side, how do the electrons move? The electrons move like that. Okay. I mean, that's not part of the notation, but I'm illustrating. Okay. Let's see, what else can we say about that? All right, there's the anode. Right. We can write the anode reaction from this. We can write the cathode reaction from this. And then if we want to write the entire balanced equation, we have to go through the process just like before, half reactions. If there's no water involved, and there's no hydrogen involved, there's none of that stuff involved, you can use, you don't even have to do the half reaction steps. If we know that magnesium, see, let me go back. There. We know that magnesium is going to do one of these things. And aluminum is going to do one of these things. Right here. Then all we have to do is balance the electrons. Right. So we need, let's see, multiply this one by 2, 6, 2, this one by 3, 3, 6. Then we can add them together. 3 magnesium plus 2 aluminum yields 2 aluminums here plus maybe magnesium. Okay, that would be the balanced equation. Now, what we would need to know in order to later on to calculate the exact potential is this value right here. 6 moles of electrons transferred. So you need to keep that somewhere. Right? Either recalculate it from your balanced equation or keep it written down in the margins of your paper or something, if you're going to use it to calculate the actual voltage. Okay. So I mentioned this earlier. If the electrode is not an active participant in the reaction, then you would need to specify what is actually used. And inert solid, usually platinum is a good one. Sometimes a graphite rod is used. In the dry cell batteries, it's a graphite rod. Goes right down through the center. It doesn't participate in the reaction, but it affords a electron transfer circuit, movement of electrons. Okay, we have a galvanic cell here based on these following reactions. All right, so let's describe the cell. Let me check my hard copy and see if any of this is animated. See, let's crack a word in here. There. Okay. All right, if we're going to put these two together, which one is likely going to be the anode? Which one's going to be the cathode? Right. Cathode is reduction, right? So the reduction would be one of them would we leave alone. Which one would we change? Well, you could look at the table and see which one's above and which one's below. But I think it's fairly evident here that iron 3+ is below, right? Because it goes from more positive to less positive and then negative. So they're probably written in the order that they appear on the table, in which case the second one would be changed negative, right? If you go based upon that formula, or if you just say, which one can you make negative and still have a positive summation? It have to be the second one. So if you change the second one to a negative, that means that iron 3+ plus electron would be on the other side. That would be the oxidation step. There we go. So we have to reverse that one, and that means change the sign and then add them together. And this cell would only produce 0.03 volts, very low voltage, or what, 30 millivolts. But it would still be spontaneous in that direction. That's the standard potential. Okay. So the electrons would be flowing from, let's see, anode on the left, right? Anode on the left. So we would have this yeah, I was just thinking for a second. We would have this on the left, 2+, right? Actually, it's not a phase change. This is an aqueous solution. So we use a comma. And this one is also an aqueous solution. Right? But you only use the vertical line if there's a phase change. There's no phase change here. But we do have platinum. Let me see. Is this one, did I draw this one out? Oh no, it should have. All right. So in that case, which one is connected to the cathode? Platinum is connected to the cathode. So you would put platinum, phase change, and then these two, right, in their proper order. And then we would need some kind of bridge. And then the other side, we would have a cathode, and it would have silver here, and then phase change to silver metal up there. And that would be your line notation for that reaction. Let's see. Oh, okay, so there's the picture version. I thought I did that. Yeah, there's our platinum electrode. You just need a conductor for the electrons. Oh,
There it is, there it is. Okay. Oops. Left out the phase. There we go. And these guys are aqueous, yep. Okay, then the silver. Okay, now we're good. That's line notation for that cell. Then we don't have to draw the picture. And again, the electrons are going to move from here over here. Actually, they're going to move from here over there. And this one is going to be converted to that one because it lost an electron. Okay. And then when it came over here, right there, this one delivers an electron to this one and it plates out on that electrode as silver metal. That's how they make costume jewelry with just a thin layer of silver on it. They take copper, usually some copper alloy, dip it in this stuff, run a current through it, run backwards so you can get silver plated out on it, and then sell it to unsuspecting. Okay. Okay, well, that's, I already said that, and I'm going to say it again. Cell potential does need to be positive in order for it to be spontaneous. We're just saying the same thing over again. Okay, so in this case, let's see, we've got silver and copper. Let's do this. We don't need that. This is the anode, which is going to be, let's see, it'll be copper, solid, and then copper 2+ in aqueous solution. There's our silver. Right, that would be our cell. And they use sodium nitrate in this one. That's all right. I mean, if the solution is made of silver nitrate and copper nitrate, then it makes sense to use nitrate salt in the bridge. Because as the nitrate travels over here to balance the positive charges that are produced when this copper is turned into copper 2+, then the anion comes out of here to balance that charge. Then if there's already nitrate there, then you don't mess with the anion balance. They're all nitrates. So that's probably one place that our lab that we're going to do next week is a little off because of potassium chloride and we've got nitrate solution. So I don't expect that to give us a problem, but who knows? Okay. So, oh, there was a question involved there, wasn't there? Sketch a cell using the following solutions and electrodes include the potential of the cell, direction of the electron flow, and labels. Okay, that's what we've done. So the voltage is going to be 0.8 minus 0.34. So the minus would be the copper reversed because this is the oxidation side. And we take that one as the reduction and subtract the value for this one. And that gives us 0.46 volts. So this one is a higher voltage than the other one. All right. Oh, what will happen to the potential if you increase the copper concentration in the anode? Okay. If you increase the copper concentration in the anode, let's look at just that side. All right. So what's happening here is the copper solid is being converted to copper 2 plus, plus our 2 electrons, which are going out here like that. Okay. That's the reaction over here. So if we increase this one, what's going to happen? Well, right, this is the direction we want to go for the spontaneous overall reaction. But if we start adding copper here in a higher amount, it's going to, well, Chatelier says it's going to go back this way. So it's going to resist the oxidation of copper, and the voltage should go down. Okay, does that make sense? Sort of. So the overall voltage would decrease. Now, of course, the E0 for this reaction is based upon 1 molar concentrations here. Right? So we would have to increase the concentration above 1 molar in order to get that effect. If we decrease the concentration to say 1/10 molar, then that would accelerate. It would be decreasing this one, right? So the reaction would move that way, and it should increase the voltage above standard. Correct? Should be, right? We'll calculate it later and see if that's true. Well, we'll calculate one of them. I don't know if it's this reaction, but we'll do it. Okay. So, of course, we have to introduce work into this whole mess. Because if we're going to send these electrons external circuit and access them, I mean, we're going to do something with them, right? We're going to light a light bulb. We're going to run an electric motor, or maybe even one of those vibrating motors like in my toothbrush, or whatever the case may be. So we need to relate cell potential to work. Well, if the system, remember, work is, we've defined work in terms of the system. If work is done on the system, it's positive. If the system does work on its surroundings, it's negative. Right? But the positive voltage says we're doing work on the surroundings because it's spontaneous reaction. So the signs are opposite. Right? So we have to do something to reconcile that. We need a fudge sign. So remember our earlier definition for voltage. It's the amount of work, remember, joules per coulomb. So the amount of work, actually in joules, per charge moved, coulombs. Now I know in the past, little q meant what? Heat, right? Okay, we're throwing a curveball at you. Now Q, we're using Q for charge, coulombs. Okay, so don't get confused. we threw a curveball at you. So in order to reconcile that charge difference, we have to say negative there. Because if this is going to be a spontaneous process, then work is going to be negative, but E needs to be positive. That means we have to put a negative right there. And if we solve it for work, then the negative work is going to be equal to the voltage times the charge transferred. Well, I think they put Q first, QE. Okay, and this is still going to be joules. This is going to be volts. This is going to be coulombs. Okay. Now, if we have a maximum potential for our cells, they won't go any higher under those conditions that we're setting. Concentration
temperature and gas pressure if it's present, then this would also be the maximum voltage where the charge is transferred would also be the maximum work that's obtained, that could be obtained from the cell. All right. Word on units of measure. So volts actually means the amount of work performed for each unit of charge that moves. And if the voltage is higher, for each unit of charge moved, we get more work out of it. Okay. So that's one of the reasons that big industrial electric motors use high voltage, like some of them are like 480 volts and 3-phase. Right, that's something else. But the higher the voltage, for the amount of charge moved, the more work you can get out of it. It's just not as safe. That's another issue. Right, I wouldn't want to get hit with 480 volts. I mean, I've felt 110 before, and that's enough. Okay. All right, that's nothing to do. All right, here's something that's a holdover from our discussion of spontaneity and entropy. You're never going to get the maximum work out. There's always going to be some loss. So this is the maximum that you can expect. And it's only maximum when the process is reversible. Right? Same concept as with thermodynamics. Process has to be reversible to get the maximum out of it. So you've got to be able to move just minuscule increments forward or reverse in order to get this out of it. And that never happens. Right? So that's one place that you lose that work, is the fact that if it's spontaneous, it's going that way and it's not reversing. And so you lose some in that process. And then there are other ways to lose it, like internal resistance. Right? All circuits have a built-in resistance. Your battery has a built-in resistance. So we can say the theoretical voltage on a cell is 2.5 volts. But when you put the battery together, you may only get 2 volts out of it, because the battery has internal resistance to movement of electrons. The only place you don't have that internal resistance is where? Superconductors. Right, at very low temperature. Superconductors are just that. They have 0 resistance. Once you get an electron moving in a superconductor, it never stops, just keeps going. Okay. That doesn't have anything to do with what we're talking about, probably, but I just thought I'd throw that in there. Okay. So if our equation is W, and all we have to do is move this negative over here, and we can say this also. W equals negative QE. This is the actual potential that we haven't calculated yet, but we will. And this is the charge moved in coulombs. And this is the work, the potential work that could be done with that process. Okay, now I told you I was going to show you how to convert coulombs to moles of electrons, because we need moles of electrons for stoichiometry purposes. So this is called the Faraday, after Michael Faraday, an Englishman who was a brilliant experimental scientist. He would go into a lab and create the simplest experiment you could possibly imagine. We have another word for it, we call it elegant. It's so simple, but it solves the problem. I mean, it generates information that's unmistakable. And he was just a master building pieces of equipment or designing experiments that would answer a question in the simplest way possible. So the Faraday, and a lot of his work he did was on electricity. And the Faraday is this value, 96,485, 96,485 coulombs for each mole of electrons. That's the equivalence. Okay. So this would be your conversion factor. And if you needed to flip it, that's fine. 1 mole on top, 96,485 coulombs on the bottom to make the conversion. And yeah, we'll do one in a few minutes where we use the Faraday. Oh, I like that last statement. This bridges the gap between physics and chemistry. Because Faraday's work was all physics. And we're interested in chemistry. Okay, now how does that relate to free energy? We've already said that a negative delta G is characteristic of a spontaneous reaction. But a positive E is characteristic of a spontaneous reaction. And a negative W is assigned to that also. So how do we relate those three terms? Well, we know that the W max is equal to delta G. W max is equal to delta G, and these are both negative. If that's negative, then this is negative. And for galvanic cell, we also know that this is true. Right? So it's like if A equals B and B equals C, then A equals C. Right? This is equal to that, and that's equal to that. So this is equal to this. Delta G was negative Q E max. And if Q is equal to the number of moles times the Faraday, right? Here's the Q, right? Charge, and this is moles N, right? So Q divided by N is equal to F, and this Q is actually this value, not just any charge. Well, actually it changes. The Q can change with the number of moles. Right? So the relationship here is the way we've written it here is Q over N, and then we want to solve for Q is NF. So that means we can substitute NF in here for Q, right? So delta G is equal to a negative NF E max. There he is. He did a lot of his best work when he was young, dude. There was I think it still exists, what they call the Royal Society. It's a gathering of brainy scientists. And if you were inducted into that Royal Society, I mean, you were on the A list, and he got in, of course. Okay. So the maximum cell potential is directly related to the free energy difference between the reactants and the products. We can say that with this expression. This maximum is related to the free energy difference between the products and the reactants. So since this positive value means, we said it means spontaneity, but we knew this one first before we got to this one, but in our sequence of chapters. So if this one's negative, right, for spontaneous reaction, and this is a negative here, And that's a positive, that's a positive. This one has to be a positive in order for that to be negative. So that's where we justified telling you earlier that a positive voltage is spontaneous. All right. So now we're going to do one of these too. It's called the concentration cell. When you set up your galvanic cell, the first time you set it up, we're going to use zinc and copper, right? Half cells, zinc on one side, copper on the other. But we're also going to set one up with, I think it's zinc only on both sides. So what would happen, let's just hypothetically, let's say we have zinc in the anode, zinc in the cathode. If they're the same concentration, what's going to happen? Nothing, right? There's no impulse to move either direction. But if we change the concentration, in this example, we've got silver on both sides. If we make silver high concentration for the cathode, low concentration in the anode, then we should get oxidation on the low concentration and reduction on the high concentration. Right? Electrodes are constructed of the same material. Solution concentrations are different. So Le Chatelier says that the lower concentration, let's write this reaction. On the left-hand side, we've got the anode. So we're going to have silver is oxidized. Silver metal leads to this ion and an electron. So this is the cathode. I mean the anode, excuse me. Anode. The cathode is going to be the other way around. Okay. Cathode. All right. If the concentration of this one is 0.1 molar and the concentration of this one is 1.0 molar, we want to know, did we set it up right? Is it going to run that direction? Is it going to go this way? Is this the electrode going to be consumed and produce those in solution? Well, when you compare the concentrations, this one is a lower concentration than that. Right? So in order for them to be more equal, then you would have to reduce the concentration here, increase the concentration there. That's what happens. And the only way you can do that is to transfer electrons because the two cells are separated. And so the only way to get that concentration to change is to consume these and plate them out on the electrode. This concentration will decrease. And this one will be consumed and produce these in solution, and its concentration will increase. Now, when will that reaction stop? When these two concentrations are equal, or that electrode is gone. Right? If you have enough of electrode here, then they will reach, eventually they'll reach equilibrium. Where you'll have, can I say they have equal concentrations? We should be able to calculate that. What would their concentrations be at equilibrium? I don't think I have a slide on it though. So we'll have to do that in review. Okay, now I promised Nernst. Walter Hermann Nernst. He was German. He worked in thermodynamics, physical chemistry, electrochemistry, and solid state physics. So he was kind of bridging the gap between chemistry and physics. And he came up with, well, several things. Let's see, he got his Nobel Prize in chemistry was for thermodynamics, where he developed a heat theorem. And the Nernst equation was his baby too. And that was the one that allows us to calculate the actual voltage for a cell based upon concentrations of solutions and the number of electrons transferred, the moles of electrons transferred. Okay, I've forgotten that one. He was the one that proposed the third law of thermodynamics. Right, remember that one? When do you have zero entropy? At absolute zero for a perfect crystal. All right, so here's his unadulterated or unmodified equation. So you want to know the actual voltage. You need to know the standard voltage. And then you need the gas constant, the temperature in Kelvin. You need to know the number of moles of electrons transferred, and you need the Faraday constant. And then you need the natural log of the Q for the reaction. So this is where we introduce the actual concentrations for the reaction. And then that also means that you need the balanced equation to be able to calculate that Q. But we have a simplified version. If we allow the temperature to be 25 degrees and not change, we just plug in 25 there as a constant. And this is constant, and that's constant, and keep this one at 25 degrees. Then we can write a simpler version. Okay, so here it is. Let's see. So we've got 25 degrees, we're going to make that constant. And then we're going to combine all these other three, and that gives us 0.0591 divided by the number of moles times log Q. And this is the one that will be used right here, because we're just going to assume 25 degrees. It's simpler that way. All right. Oh, by the way, I left one thing out. Minus 0.0591 over n. We're going to use common log of Q instead of natural log. And that little box on the right is just a proof. A proof for converting this one to this one. And that value, 2.3026, is incorporated in here. Did I put that in there before? Yeah, there it is. Right here. So that also goes into this 0.0591. So then we can use common logs instead of natural logs. Okay. Those are the major differences. And this is the one that we're going to focus on. Now, if you get into a situation where you're at some point in the future, who knows where we'll be in the future. If you find yourself in a situation where you need to, your temperature's different, and then you can go back to the original and use it. Okay, so here's another possibility. Suppose we are at equilibrium, right? Where this is K, right? Instead of Q for the balanced reaction. What if it's actually K? Well, if it's K, what happens to the cell? What's the voltage on the cell? Big zero. No voltage. If you're at equilibrium, there's no impulse whatsoever for electrons to move, right? Okay. So in that case, we can substitute K in here. And this would be 0. Right, and this would be unchanged. Over there. So now, if we're at equilibrium, we can solve our equation for K. We can actually determine K based upon the standard voltage for the E0 for the cell. And that's what this calculation does, right? It sets this to K and this to 0, and then we solve and we find that E0 is equal to 0.0591 divided by the moles of electrons transferred times the log of K. So if we know this value and we know this for the equation, we can calculate what the K is. Right? Another way of finding the equilibrium constant for that reaction. In here. You're liable to see one of those in your review document for sure. All right. What's wrong button? Okay, here's an example. We got another hour. Here's an example. For this oxidation reduction reaction, the appropriate half reactions are given there, and the reduction potentials are given. So we want to balance the redox reaction and calculate the E0 and then calculate the K. Right? So in order to get the standard potential, which one reverses? Well, the one that gives us the positive value. Right? So we reverse the chromium one, and we have to multiply it by 2, of course, to get the number of electrons transferred. So we have 2 moles of electrons transferred. And the standard potential then is 0.67 volts with the chromium as the anode and the S406 as the cathode. Right? And then this is the balanced reaction. Right? Let's see. Yeah, that's balanced. We didn't have to add any water in there. Now, if we had done this half reaction balanced, I would be willing to bet that the waters and the hydrogens and anything else we added in there would have canceled out. So this is the balanced equation. Right here. Here. There it is. So in this reaction, N equals 2, right, for our Nernst equation. And we're going for K, right? So we don't have to calculate Q. We're going for K. So if N equals 2, then we can solve our equation for log K and substitute the E0, which we determined as 0.67, and 2 is a number of moles, and we get the log of K is 22.6, and then K is 4 times 10 to the 22. So what does that tell you about this reaction? It's definitely to the right. Like 10 to the 22, that equilibrium is way to the right. And we could use K to calculate delta G, couldn't we? We know how to do that. Is that one of our, did I do that here? I just thought of it. I don't know if I put it in here or not. No, I didn't. We could calculate delta G, couldn't we? I have to refresh my memory on the formula. Delta G0 is minus RT log K. So we could do that. Minus, let's see. Delta G minus RT log K. Okay, so we could put this value in here, 4 times 10 to the 22nd, take the natural log of it, times 298 K,
right? Times 8.4, let's see.
What's that value? 8.41, 8 point. Can't even remember. 3145, right? Okay. And negative. We could calculate the delta G for that. All right. This is actually common. Large equilibrium constants are common for redox reactions in the spontaneous direction. 4 times 10 to the 22. It's massive. So what's the difference between E and E0? Well, E0 is standard, right? 1 molar concentration, 1 atmosphere pressure on gases, and 25 degrees Celsius. So what's E? E is the actual potential based on the concentrations that you're given. And if the temperature changes, different temperature, different gas pressures, whatever if they're part of the reaction. So when is E equal to 0? At equilibrium. Right, it's a dead battery. That's equilibrium for a battery. Sometimes you can bring them back, sometimes you can't. When E0, when is E0 equal to 0? That's for a concentration cell. For a concentration cell, E0 under standard conditions, both cells have to be 1 molar. Right? So for a concentration cell, E0 is always 0. It only changes, it only becomes some other value for E if the concentrations are different. Okay. Furrowed brows. Okay. Right, because they've got the same values for a cathode and anode under standard conditions, which is equal to 0. Subtract one from the other, you always get 0. All right, a concentration cell is constructed using 2 nickel electrodes with Ni2 plus concentrations of 1 molar and 1 times 10 to the minus 4th molar in the half cells. So the cathode is going to be the more concentrated one. It's always going to be on the right. And that's where a nickel is reduced to nickel solid. So notice the subscripts there. I've got C for cathode and A for anode. The anode is where the nickel is going to be consumed and converted into electrodes so you can free up the electrons to move to the next other cell. Okay. So that's the low concentration. So what are the concentrations? Well, we're given the values right here. Right. So the anode is going to be the lowest concentration, 1 times 10 to the minus 4. Cathode is going to be 1. 0.0591, and then the number of moles moved is 2 moles of electrons. So the concentration cell should be 0.118 volts. Right, and that's typical. Concentration cells typically have much lower voltage than if you have 2 different reactions for your half reactions. You have the same reaction and it's a difference in concentration. They're typically much lower in voltage. Right, measured in millivolts. Actually, this is 118 millivolts. Actually, that's pretty high. And the reason it's really high is because the difference in concentrations is 4 orders of magnitude. Right. They just barely have enough nickel ions in the cathode to make the reaction go. If it didn't have any in there, it probably wouldn't go at all. I don't know if that's true or not. What would happen if the initial concentration was 0? Then the voltage would be 0, wouldn't it? Based on the calculation, right? if the anode, the low concentration were actually zero, then that would be zero. And log of zero is what? Zero. Right, 10 to what power is zero? That's a good question. What power of 10 will give you zero? Zero, if it's zero power, it'd be one. Right? Doesn't exist. Well, I have to ask a mathematician. But the reaction would, the log of zero is nothing. So you wouldn't get anything. You got to have a little bit of nickel in there. So we could go down to 10 to the minus 5, 10 to the minus 6. Probably boost the voltage up some. I don't know if we'd ever get it up to 1 volt or even a half a volt. Okay, enough speculating. Let's move on. So let's say you make a galvanic cell, 25 degrees. The nickel electrode is 1 molar at minus 0.23. And the silver electrode is plus 0.80 at 1 molar. All right. So sketch out this cell, labeling the anode, cathode, showing the direction of electron flow, and calculate cell potential. Well, which one's going to be, these are standard reduction potentials. So which one's going to stay reducing? Well, look at the way they're arranged, right? If you change the 0.8 to a negative, you get a negative, and that's not spontaneous. If you change the nickel sign to a positive, that means reverse its direction, then you get a positive. So the nickel should be the anode, correct? Nickel should be the anode. You're going to have nickel, 2 plus, yeah, 2 plus. And nickel electrode. Okay, and in this one, you're going to have silver, right? Silver, 1 plus. And you're going to have a silver electrode and connected through some kind of meter, I guess. And then you got a solution here, like that, and you're going to have a salt bridge. Okay, the electrons are going to flow this way. That means the nickel is going to be oxidized. Right. Nickel, 2 plus 2 electrons. And this side is going to be reduced. So silver plus an electron yields. Okay. And the E0 is going to be equal to 0.80 minus a minus 0.23, which should be what? 1.03 volts. Okay. Oh, I didn't do the line drawing. Okay, so anode first. And nickel here, solid, phase change, nickel 2 plus is 1 molar, and then the salt bridge, and then we have the silver 1 plus, aqueous, and phase change to silver solid electrode. There you go. Okay, there's our drawing. I think I have everything right. Not as pretty as that, but works. There's the cell potential, standard cell potential. Oh, that's it. That's all they wanted us to do. Okay. Now, other types of galvanic cells. Here's the lead acid battery. Notice that we don't have a salt bridge. We just have the plates. Right? One plate is solid, is pure lead, and the other plate is pure lead, lead 4 oxide. Right? The lead 4 oxide is the cathode, because the lead in that one is
4+. And we're gonna add some electrons to it and make something else. And the other one is the anode. We have lead solid, and it's going to produce electrons plus something else. I think it's a 2+. So they're both producing 2+ lead. And that is in the solution, the sulfuric acid solution. So it's going to be a lead 2+ sulfate. So it's going to be a sulfate. This is the counter anion for both of them. That's why you don't need a salt bridge, because they share this in common with both reactions. There's the overall reaction. We've got the lead oxide, lead. This is lead 4 oxide and sulfuric acid. And then the sulfate is counter ion for both of them. So that's the overall reaction. We would do the half reactions and then we can balance it and pull them back together just like we did before. No need for salt bridge or porous membrane. And that's good for compactness, right? Of course, it's not good for weight, right? Lead, I mean, what does lead mean in Latin? The plumbum, what does that mean? That's Latin for heavy. Right? It was appropriately named. Right? That's why we don't put lead acid batteries in electric vehicles. That's too heavy. Right? You can't get enough power out of them to run the thing. Most of it's wasted in moving that heavy lead. That's why they use lithium ion for now. We're working on other alternatives like the hydrogen fuel cell. Be a good alternative if we could ever perfect it. They're finding with these fully electric vehicles now, with the electric power prices spiking all over the country, especially in California, they deserve it. Is that it's costing more to run their electric vehicles than it would if they had stayed with gasoline. A hybrid's a good idea. Yeah. Too expensive for me, but I mean, it's a good technology. All right. So when the battery runs down, what do? Well, you drive the voltage backwards, just like that potentiometer. You drive it backwards, and you drive this reaction back to lead, drive this reaction back to lead 4 oxide, and the battery's recharged and ready to go again. There's just one problem. Lead sulfate is not soluble. So where does it end up? It ends up on the electrodes. So lead 2 sulfate coats the electrodes. And then when you recharge it, that puts it back into solution as sulfuric acid, and then the lead goes back to the plates. But you reach a point after so many cycles that there's still some lead sulfate left on the plates each time you run through a cycle. So eventually you get to the point where they're coated with lead sulfate and they can't reach the solution. It's a physical block on the plates. And at that point, the plates are said to be sulfated out. And at that point, you cannot recharge the battery. It is dead for good. The only thing you can do then is recycle it. And then the manufacturers, factories that are set up for that can separate the two by other means. Separate the lead out from the lead and reuse the material. So that's another reason for recycling your lead batteries. Not just to avoid pollution, but because right, how much energy and what's the cost of getting lead from ore? It's a certain amount of cost. What's the cost from getting lead from recycled materials? A lot less. So there's economics involved. Okay, this is a diagram of your dry cell battery. Remember I said the
the graphite rod was not part of the reaction. It's just a conductor, right? And that is at the cathode. And the cathode reaction takes place in this paste. They call it a dry cell, but it can't be completely dry, because if it's dry, then the ions will move. And then the anode is the casing of the battery. The casing of the battery is zinc here. Right? And it's covered with a polymer on the outside, right? So it's not exposed to the environment. And it won't get you shocked, it will short circuit. So let's see. So this is the positive end and this is the negative end, right? So the negative end is where electrons exit. So the anode, yeah, the electrons exit here, they go through something and they come out and they go back into the positive here and into this matrix to complete the cathodic reaction. Okay, there's something that we don't talk about. I haven't heard talked about in chemistry, is the measurement of current. When I took physics, the measurement of current was, well, in the beginning, they didn't know what they were doing, right? They knew electricity and they knew it was positive and negative differences, right? But they didn't know which way the current moved, right? The charge carriers, they didn't know about the electron. So somebody decided, okay, the current travels from positive to negative. Okay, they got it wrong, but we're stuck with it, right? From physics perspective, the current moves from positive to negative, but we know the current carrier is electrons. So the electrons move from negative to positive. Right? Just in case you run into that problem, in chemistry, you probably won't. But if you get into physics, then it might flip your head around to recognize that's the truth. Okay. All right, I've already said that. Here's another type of battery, a mercury battery. It's got a mercury 2 oxide in a paste. And the anode is the zinc container. And cathode is just a steel plug. You'll see these in, well, you won't see them anymore because they got mercury in them, right? They've substituted something else for them. But these types of button batteries you'll see in small devices like hearing aids and watches, calculators, but it'll be a different, it won't have mercury in it, it'll be a different chemistry. And that's fine. There's plenty to choose from. This is the fuel cell that I mentioned earlier. So the fuel cell has 2 electrodes like any other galvanic cell, only the reactants for the cathode and the anode are continuously supplied and removed. So you've got oxygen coming in one side at the cathode, and you've got hydrogen coming in at the anode. And when they combine, you get electrons moving up this way, across to that way. And this porous carbon electrode also contains catalysts, right? Because this reaction, while it is thermodynamically favored, it's spontaneous. It doesn't happen very fast. So catalysts are in there to make it move. That's kinetic. We combine kinetics and thermodynamics here in one technology. And this reaction, when the fuel cells were originally designed and proposed and then used, they were first used in spacecraft because they already had oxygen for their astronauts to breathe, so they could use some of that. All they had to do was carry some hydrogen with them, and then they could combine that in the fuel cell and continuously supply power for the spacecraft, whether you had sunlight or not. Right? Solar cells be damned, so to speak. But the problem with the technology was, this reaction takes place at very high temperature. So you've got to take care to insulate it from everything else. And that's one of the problems, not the only one, but one of the problems for this technology making it into motorized vehicles. It's because of that temperature. They brought the temperature down a good bit, right? But there's still other problems, like how do you store the hydrogen in a moving vehicle? You don't put it in pressurized tanks at 2,500 psi. Right? That'd be stupid. So they're working on other technologies where you can store hydrogen in the tanks at just above ambient pressure. But they haven't quite mastered it yet. So there are economics involved. I'm sure EPA and OSHA got involved. But they always do. Federal government has to stick their nose into everything. But it's a very efficient technology. Let's see, we got to do some electrolysis. First we're going to do corrosion, right? Corrosion is a spontaneous process that takes a metal and removes electrons from it. And so the most commonly identified corrosion is iron going to it would be 3+, 3+. That reaction. Now, if we include the rest of the reaction, this is only half reaction. If we include the rest of the reaction, it's going to be oxygen. Right? And this will be Fe2O3. So we need 2 of these, and we need 1 of those. 4 of these, 2 of these, 3 of those. 6, 4. There we go. So that would be the overall reaction of corrosion of iron to rust. That's what this is, rust. And it's a problem. Right? And it's accelerated if you can facilitate the movement of electrons. So salt water works better than fresh water because fresh water is essentially, pure water is an insulator. It's got no mobile electrons to speak of, other than the acid base, typical 10 to the -7th molar hydrogen ions, 10 to the -7th molar hydroxides, pure water. But if you've got salt water, you've got all those sodium ions and chloride ions in them, and they can facilitate the movement of electrons like crazy. So steel hull vessels out in the ocean are in constant risk of corrosion. And so they try various things like painting them, right, sealing them off. There's another way to do it, and we'll mention it in a few minutes. It's called cathodic protection. But this oxidizes the metal. This is corrosion. That's the definition of corrosion, where your metal oxidizes. On the surface of steel or on the surface of iron, you actually set up a galvanic cell where the water hits it. And so you get the anodic section, of course, is where the metal is consumed, right, on the left-hand side of our thing, and on the right-hand side, you produce rust. That's the cathodic side. Actually, go back. I left out water. Right. Water goes into this reaction. Well, I'm not going to write the rest of it. It's up there. If we balanced it by half reactions, we would end up with water and hydroxide. So this would be under basic solution, wouldn't it? We'd have to convert it to basic. Okay, ways to prevent corrosion. Galvanizing is one way, right? When I was growing up as a kid, that's about the only way that you knew. There were galvanized buckets everywhere. right? And you can tell a galvanized bucket because of the weight. You just take a steel bucket and dip it in molten zinc. That was it. It covered in zinc, and you let it drip, and you can see places around the bucket where the drips, right? The metal came off of it and froze. And you can see those what would you call them? Crystal patterns, right? They'd be kind of angular. You ever seen a galvanized bucket? No. Anything that's galvanized? No, I guess not. It's pretty, actually. But what it does is it protects the underlying metal by sacrificially oxidizing the zinc. Zinc is a more active metal than iron. So zinc is more likely to become oxidized than iron underneath. It's a sacrificial process. And since it coats the steel, when the zinc turns to oxide, it gets kind of gray, and a new bucket will be shiny. But a bucket that's been around a while will turn gray. It forms a layer of zinc oxide on the surface, and that blocks any water and oxygen from getting through to the underside, and that's an added protection. Alloying, stainless steel, right? Chromium and iron and carbon were the original components in stainless steel. And the chromium actually was pretty high. It was like 35% by weight in the original stainless steel. Now they've got it down lower than that. It's like 15 to 20% because they add other things in there. They find they don't need that much. But this was the original stainless steel. And what happens is chromium is such a reactive metal, so much more reactive than iron, even in the alloy. What it does is the chromium reacts almost instantly with oxygen in the air. It produces chromium oxide on the surface, and that seals the surface with a very thin layer. It's so thin that once you polish it, you scratch it, you can't even find the scratch, or the scratch is not that evident because it seals like that. There are other ways to alloy. Ships, naval vessels used to make everything out of brass. You wouldn't use steel unless you had to, but wherever you could use brass, copper and nickel, right? They would have that same effect. They would seal off from the external environment. They would not corrode any further. I'm not sure which is which, copper, probably the copper. No, zinc. Zinc is more reactive than copper. So zinc will do the sealing. But it's also an alloy, and an alloy of copper is stronger and more durable than copper itself. Right? Think of the history, world history. Right? Got the Stone Age, right? Then you have the copper came in as think of it in terms of weapons, like throwing rocks at each other, and then making your swords out of copper, right? They weren't very durable. And they put some tin in it, made it much stronger. So you had for a while, during the time of the Trojan Wars, everything there was bronze, right? And then came along with steel. And they say one school of thought says the steel came into being probably through the Philistines, right, along the coast of Israel. And, you know, David and Solomon, all those were king. They had to deal with the Philistines, and they got hold of their steel technology, and that helped them out. Anyway, these alloys are stronger, make stronger metals than just the pure metal. Right? Pure iron, you can scratch it with your fingernail. Right? Put a little carbon in it, and you got steel. It doesn't take much, right? 0.2% is mild steel. Cathodic protection. This has been used for buried tanks, like gasoline tanks, to protect them from corrosion. So once you put them in the ground, you know, they're in constant contact with water, and they're going to corrode. So what you do is you connect a more reactive metal through a wire to a big chunk of this reactive metal and bury it in the ground. And it serves as the anode right? It corrodes and releases electrons that go back to the steel tank and turn the tank into a cathode, where the electrons, any corrosion that tries to happen with the steel is counteracted by those extra electrons that take that and turn it back into iron. So that's the cathodic protection part. I think I got a picture of it. Yeah, there we go. So the magnesium in this case is the anode, the buried pipe is the cathode. And every water tank has an anode in it. You ever had to replace the anode in your water tank? When I first moved into my house, it didn't take but a few months, and I started seeing coming out the faucet, little flecks, the hot water faucet, little flecks of what looked like metal or oxides of metal. What was happening was I think it's aluminum. The aluminum anode in that water tank is there to protect the tank, and the anode corrodes. And I have all copper pipes in my house. A lot of houses don't do that anymore, but all copper pipes, and the copper was setting up a reaction so that the tank would have been in danger. Now, it wouldn't have been in too much danger because now all water tanks are lined with glass. But the fittings and all that stuff would have been in danger, and as the water passes through the pipes, you would still get some electrolytic processes, galvanic processes. So this anode is there to protect everything else. The anode sacrifices itself. And I was getting, the dishwasher had this little screen in it, right, to filter out big chunks of stuff. Well, it got clogged up and wasn't working anymore. So I pulled it out and found this filter in there, and it was covered in those little flecks of aluminum oxide that had come from my anode. Once the copper pipes developed a corrosive film on the inside, then they stopped doing that. And all I had to do was replace that anode once, and that was good forever. Well, then the tank went kablooey and I had to replace it. So we started all over again. So that's cathodic protection. All right, so coatings, alloys, cathodic protection are ways to protect the buried pipe. Now for electrolysis. Oh, another place that you'll see an electrochemical reaction is on, you know, any houses or buildings around here with copper roofs? No. The campus of Louisiana State University had lots of buildings with either copper roofs or tile. That was their architectural mode. The Coliseum, not where you play sports, but where you have animal shows, right? The agricultural Coliseum had a copper roof on it, and they replaced it one time because it was too corroded, and I think probably the rivets were coating out and they were dropping shingles on the ground. So they replaced it, and it started off just beautiful, bright, shiny, that copper color. And it didn't take long where it started to get dull, and then it looked kind of ugly. But I was there for several years. I was there for 13 years. Eventually it turned a nice blue-green. And that's what they call the patina, copper patina. You go places in Europe that have roofs that are hundreds of years old that are still made out of copper. They've got a gorgeous blue-green color. And it's formation of carbonates and sulfides of copper. Right? It's an electrolytic process. It's an electrochemical process. Okay, electrolysis, where we're going to run the reaction in reverse. All right, so how do we deal with that? Well, here's one example. Right, if you take water and you run a direct current through it, you can split the water molecule into hydrogen and oxygen. Well, you know that an electrochemical reaction has occurred, a redox reaction has occurred, because hydrogen is +1 on the left and now it's 0 on the right. And oxygen is -2 on the left, and now it's 0 on the right. Okay, so you know that a redox reaction definitely occurred. And it occurred not in the spontaneous direction, because that would be hydrogen and oxygen making water. It's in the reverse direction. So we're adding a voltage into this water that exceeds the standard potential for oxygen and hydrogen reacting. We're running it in reverse. Okay. So when you do that, you get hydrogen and oxygen. And this is what would be required if we were going to run the economy on hydrogen, right? With the fuel cells and those types of things, we would need a source of hydrogen, and we've got a ready source in water. All we need is a cheap source of electrical power, and that's nuclear. You're not going to get a sustained source of power that's cheap with fossil fuels, not with like fluctuating prices the way they are, and different politicians coming in and hammering your products, like the current administration does, and is responsible for our inflation right now, 100%. So that would be the holy grail of a hydrogen economy, is making hydrogen out of water. So the stoichiometry of electrolysis hinges on knowing how much current is being passed through in the reverse direction and how long it goes. Because current is equal to charge transfer per unit time. And this charge would be in coulombs, and this time would be in seconds. So 1 coulomb per second is 1 amp. You heard about amps, right? Yeah. Okay, so that's where you would start with an electrolysis problem. And it's basically, if you understand, if you have the stoichiometry, the balanced equation, because you're going to need it. You're going to need the balanced equation to answer this question. Oh, there it is. You're going to need moles of electrons transferred. That's where you need the stoichiometry. Beyond that, it's just unit conversions. It's dimensional analysis. It's electrolysis. Okay, so here's an example. Of converting coulombs of charge into moles of electrons. Right, there's our conversion factor right there. That's Faraday right here. Right, so here's an example. An unknown metal is electrolyzed. It took 52.8 seconds. Let's put it up here. Time equals 52.8 seconds for a current of 2 amps. So the current, which we designate as capital I, is 2 amps, which is equal to 2 coulombs per second. To plate 0.0719, so mass plated is 0.0719 grams of that metal, our unknown metal, from a solution containing this CHEM102. Right. So this is our unknown. We do know the charge because nitrate is -1. So the metal is a 3+. And we're going to plate it out as a solid, which means we need 3 electrons for each mole of metal. Okay? So if we're going to identify the metal, we need to know its molar mass. We can't get the number of protons, right? It's Z number, right? But if we know the molar mass, we can find it up here probably.
So we got the mass. We just need, how many moles does that represent? How many moles of metal? Right? So we need to know moles of electrons, then we can convert to moles of metal, right? Because now we have this reaction. This is our stoichiometry. So if we have 52.8 seconds times 2 coulombs per second, right? That cancels the seconds. And then we're going to convert coulombs to moles of electrons. So 1 mole of electron is 90 something. You remember the number? Probably in the animation, but I'd rather do it without that right now. 96,485. 96,485 coulombs per mole. Get rid of coulombs. Now we have moles of electrons. Now we want to convert moles of electrons to moles of metal. So 3 moles of electrons is 1 mole of metal. So that tells us how many moles of metal we have. Correct? Get my calculator. All right, 52.8 seconds. That's the thinking part. This is just number crunching. 96,485 divided into that, and 3 divided into that is okay. So now molar mass would be mass per number of moles. We have 0.0719 grams per 3.65 times 10 to the minus 4 moles. Here we go. 0.0719. I get about 218 grams per mole. Well, let's see if we can find 218. Let's see. These are 100s. These are 100s. Okay, 200. 218. Where's 218? Did I do that wrong? Because I don't find it. All right, let's see what I did wrong.
Everything's right. You just didn't calculate it, I guess, because it says 9197,
Oh,
but everything else is right.
okay, let me do it again. I was just using the numbers in my calculator. Maybe I punched them all the ways. 0.0719 and 3.65 exponent minus 4. Yeah, 197. I was too trusting of my calculator. So 197 would be gold. Woo. There you go. We plated out gold, probably on fake jewelry. Okay, let's get more animation. There we go. Yeah. Well, you were looking at the cheat sheet and I wasn't. Okay. So now we've got a solution with these different metals. What are we going to do with it? That's the question. Okay, I got 15 minutes. 0.1 molar of each of these. I got lead 2 plus 0.1 molar. We got copper, tin, and nickel, and we got zinc. Okay. Predict the order in which the metals played out as the voltage is turned up from 0. The metals form on the cathode or the anode. Where do the metals form? On the cathode or the anode? Exactly right. Yep. Okay, so that means we've got plus 2 electrons. Actually, each one has 2 electrons. and produces the associated metal. Nickel, tin, copper, lead.
So in order to tell what order they played out in, we need to know their potentials. Okay, here we go. Side of reduction potentials, predict the order of plating. The more positive standard reduction potential plates first as the voltage is increased. Because it's just the reverse of what we would expect. If it were a spontaneous reaction. The reverse voltage would have to overcome the negatives, the lower ones, with higher voltage than it would with the pre-existing high voltage. So the more positive standard potential plates out first. Okay. So there's copper. There's lead. All right, copper goes first.
Lead goes second.
Keep going.
Tin goes third.
Nickel goes fourth.
And that means this was the fifth. So they're almost in order already. Copper was first.
All right. Just a little history lesson now.
Aluminum, we take aluminum for granted now. Aluminum is a very, very reactive metal with oxygen. The ore from which aluminum is made is, the ore is called bauxite, but this is the compound that we want to separate the aluminum ions from and make them into metal. And it takes a lot of energy. In fact, when aluminum was first discovered and was beginning to be produced by chemical means, it cost more to do that than the price of gold. So Louis XIV, when he served his big state dinners in Versailles, everybody had aluminum utensils because they're more expensive than gold. It wasn't until let's see. It wasn't until a man by the name of Hall. In fact, he was a young man. In fact, he was like just graduated from high school and was going into college. His first project in college was to figure out how to produce aluminum cheaply. In fact, he started working in his parents' garage, and boy, did he make a mess. Eventually, he figured it out, and he used electrolysis to do it. It takes a lot of electrical power to do it, but it's much, much cheaper than the chemical process that Louis XIV had to rely on. Right, so that's why now we can make aluminum foil and wrap our food in it and use it once, throw it away. It's so cheap. But you need a lot of electrical power. That's why aluminum factories that produce aluminum from the ore are situated in places where you can have cheap energy, like Tennessee Valley Authority, when they dammed up the Tennessee River through Tennessee and Kentucky and northern Georgia and parts of Alabama, and produced hydroelectric power. Government was paying for the facilities, so the power was free. I mean, it was whoever ran the place, it was all profit. So they electrified the nation, that part of the nation, through the Tennessee Valley Authority, and then places where you have plentiful coal, right, in southern Pennsylvania and Virginia and West Virginia and parts of Kentucky and Western Virginia. You can produce electricity reasonably priced, and Alcoa situated their factory in southwestern Pennsylvania.
And they would just ship in the bauxite from the tropics, come from the Caribbean primarily. And what they would do down there was they would dig it up and then do pre-processing, like to move all the clay minerals and all that stuff, and just send this almost pure aluminum oxide to the factory. And this is what they would do. In order to process the bauxite, it would have to be melted, right? Solid ionic compounds will not conduct electricity, and it's impossible to get them apart. So you have to melt them. Well, this was the trick that Hall had used. He found that if he made an alloy, if he put aluminum oxide together with sodium aluminum fluoride, it would lower the melting point considerably, take less heat to get it to melt, and it wouldn't interfere with the electrolytic process. Right? And then the aluminum, of course, would be, when it was electrolyzed, it would just sink to the bottom of the container, and they would just knock off the plug, and out comes the liquid aluminum. And all they would have to do is periodically change the carbon electrodes, the graphite electrodes, because they would be consumed in the process. Oh, there it is. Aluminum oxide melts at 2000 degrees Celsius. But when you add sodium aluminum fluoride to it, it will melt at 960 degrees, which is pretty hot, but it's not as hot as the other, and it takes less energy to get there. Okay, you can also electroplate your spoons. Actually, have you ever seen corroded silverware? I mean, true silverware. They don't sell it anymore. It's all stainless now. But my mother used to have a set of silverware that she got as a wedding present. It was in this nice mahogany colored box. We would only bring it out for special occasions. But you could, it would become corroded, and you had two choices. You could use a silver polish, and polish it off. Or you could take a baking dish and line it with aluminum foil and fill it with water and throw some salt in it and drop your silver utensils on there in contact with the aluminum. And over time, the electrolytic process would convert that corrosion, that oxides of silver, to silver metal, because aluminum is more reactive. And you can watch it happen. I mean, it happens really quick. If you ever have a corroded silver dime, you need a dime that's let's see, when did they start adulterating, debasing currencies? 72, I think. Yeah, I believe it was 72, where they went from 90% silver coins to silver-clad copper. But if you can get a coin that's older than that, it's probably going to be corroded. And you can do that trick and just drop it in there and watch it turn bright color again. So that's this is one way to do it, where you replate silver. And sodium metal and chlorine gas are essential industrial elements. And the way we produce it is we electrolytically split sodium chloride. Just melt sodium chloride salt and then run a current through it. I mean, a very, very, very high voltage current through it, lots of amps. And you split off the chlorine gas is collected at the anode, and sodium is collected at the cathode. And then it goes on to other processes. You sell it to another company to do the things. They take the sodium, take the chlorine, take the sodium and make sodium hydroxide out of it, add it to water. Take the chlorine and oxidize that to hypochlorite. Well, actually, you take the chlorine gas. Yeah, take the chlorine gas, bubble it through your sodium hydroxide, and it produces sodium hypochlorite, bleach. I think that's it. Yeah, that's it. I have 3 minutes to spare. It only took all morning to do that. Okay, next Monday, we'll look at the review document and get ready for a final. Well, technically, it's a final during finals week, but it's only on this chapter.